There's Mark. Hello, Mark.
Hello, everyone.
Yeah, people are connecting. I think, well, I can introduce myself for a start. Thank you for coming. I'm Carlos Westendorp. I'm from the Computing Specific Services for research. And I'm also part of this IAC-DEEP, the machine learning group of the IAC, where Mark and Andres are the IPs, okay? And we're a couple of staff members also belonging to this group. And there's a lot of, I think, Mark, and you can introduce the group.
Yeah, so I just want to say, well, thank you all for coming. I cannot see the room, but it looks full. I apologize for not being there. I'm at a meeting and just want to take 2 minutes just to say what Carlos was saying, that for those who don't know, there's a machine learning AI group at the ISC, which has been running for a few years now, led by Andres and myself. There are students, postdocs, and also several staff people like Carlos. And we usually meet once a week. We've noticed, so for this year, so we've noticed that sometimes, the learning curve for ML is complicated and getting people into our discussions is not easy, but there's lots of interest on people wanting to use AI. So we thought for this year, we could start this new experiment, which is trying to get some lectures or on specific techniques or AI state-of-the-art methods that people at the ISC use for their research. And so the idea is to run this over the year, globally once a month, in which we will present different methods, hopefully in an affordable way for everyone. And the lecturers will be, as I said, people from the group, so grad students and also postdocs working in the group that will present what they are in an affordable way, the different methods. So I hope you enjoy. So this first lecture is by Carlos, and he's going to give an introduction on neural networks. And again, if you are interested in our activities, just get in touch, and then you can also join the group if you're interested. Yeah. Thank you, Carlos.
Okay, thanks. Thanks a lot, Mark. Yeah, the idea, well, there's a lot of postdocs, a lot of students also in the group, and there's people who are interested in machine learning in general. But some people just don't have the time, or they just don't have the knowledge or anything to get into deep learning. And we're going to give these lectures. They're brief lectures. I'm going to show you the course schedule in a moment. And well, it's a great poster from Marina that shows what we want to talk about in general terms. The next talk is Marina's about convolutional neural networks. And it's going to be, this is the schedule, if this works somehow. Let's see if it somehow works. To check how this should be. This always happens. Yeah, the shift happens, like we say in the computing world. Let's see if I can find myself where I am. Somewhere here. Okay. Well, this is the course. Okay, this is the first course. It's going to be short, less than an hour, I hope. And you can ask me whatever you wish. The thing is, I set this up well also with Mark. He had a great idea for the introduction. And I'm putting, the idea, at least for me, is to put some code, some sort of boilerplate, simple code somewhere. This is my GitHub, the personal GitHub. I'm going to show a few Python notebooks. So people can use this code. This is going to be very simple today, but in the future, there's going to be more complicated networks. So you can just take the network and apply it to your data. That's it. So you don't waste time trying things out and starting from scratch, because we've already done that. And in the group, there are many great people who are experts in images or in spectra or whatever, and lots of things, okay? So the course is going to be, the introduction today is going to be quite basic. I hope you get some intuition about how neural networks learn and a few key concepts that you have to take away so you're ready for the next courses. The next one is going to be by Marina on the 25th of November about computer vision using convolutional neural networks, CNNs, okay? And then we're going to go on next year with statistical deep learning, okay? In the different parts, those are going to be a few lectures. And there's going to be sequences, neural networks for sequences and time series, which are very interesting. And also neural networks for unstructured data, for graph neural networks. And at the end, we're going to talk about foundational models, self-supervised learning, lots of things, okay? Each course is self-contained in a way, and it's going to be so you can get some takeaways and some ideas that you say, okay, I can apply this to my work, and I'm going to take the code and use it, okay? So to start with, this is the general problem we have in astrophysics. For those who are not astrophysically related, we have very strange units, okay? The temperature is at the bottom, and it's higher to the left, and there's a magnitude, which is, okay, higher to above, but it's a logarithmic scale. But it doesn't matter. It's any old dots, okay? And we have a problem. We want to make something out of this. So what do we do? How do we apply machine learning to this? Well, there are two different approaches. Either we know the physics underneath, which we don't in most cases. It's nonlinear and it's really strange. Well, here we know the physics because I made this data up with very simple equations. I'll show you later. But if we don't know the physics, we only know that the higher the effective temperature for the stars, well, the higher, the brighter the stars are. So it's a straight line. If we don't know anything else, like I teach my students in the first grade, if we don't know anything else, just apply a straight line. Why apply a polynomial when you don't know what the physics is? Or we can do something else. We can go to the data. What the data is telling us about the underlying function, the underlying reality. And that's a big thing. That's a big jump. Okay. So if the physics is somehow, there's no suitable physical model, which is going to be the case in most times because it's really, really complicated. And we want some accurate prediction, or the physical model, we know the physical model, but it's nonlinear and it's too complex, or the data set is too large. And we want some speed in applying this solution to the problem. Or we even want to find some hidden information in the data. The data has some information, which the equations, as we have them, don't solve doesn't reveal this information, okay? So we want to make a discovery. This is the case for astrophysics, and it's great because we need large and complex data sets where machine learning is going to work. So it's exactly the field where we should apply this type of approach, okay? We're going to talk about supervised learning for a start, and it's a very simple problem. It's the same problem, only in vectors. Okay, we have a training set where we know the features, we know with the measurements, we know the magnitudes or the fluxes or the colors, whatever your astronomical objects are. Okay, and we have a specific labels like effective temperature in my case, or we have the morphology for galaxies, for instance, the object type, redshift, distances, whatever. Okay, but we know those labels for those objects. How do we know that? Well, we suppose we know. Okay, and the thing is, we want to find a function that, given an unknown set of values, we want to find those labels for this unlabeled set. We want a general function, an f function that has some parameters, w, we call it w, where if you have an input feature, it gives you an output label. Okay, this is supervised learning. How are we going to do that? We want to find that f, that function, general function, for unlabeled. We're going to train it on a labeled set, or where we know the values, and we're going to use it on an unlabeled set, where we don't know the labels. And when we apply this function, we want to find the labels for this unlabeled set. So it's a general goal where this function has to be nonlinear, because otherwise it's boring. I mean, we know how to fit straight lines. So if it was a linear problem, well, we finished here. But we want non-linearities, which is the great thing, you know, about these the strange physics that is behind every object in astrophysics. Okay, so we want to find a nonlinear function that output the correct value for an assigned input object. The problem is this function, this f, has a lot of parameters. How are we going to find those parameters? Okay, well, we have a minimization problem. We want to find that set of parameters in which the prediction error is minimal for all unseen vectors. Okay? So when we put some value that we know, it gives you an output, and this output has to be very small, but that's a training set. We want to find that for the test set. The test set is the one that has never seen any algorithm, and we have to predict it with enough accuracy, okay? And it has to be, the error has to be minimal, okay? So the problem is twofold, okay? We want to define a loss function. The loss is the difference from the real labels, I hope the cursor works, from the real labels to the predicted labels. We can use mean square error if we want to not be sensitive to very distant, very high outliers. We use something like the mean square loss. Mean square error loss, which is very simple to calculate because it's the error, and then you take the square, and then you take the mean. So it's very easy to find out. There are other types of losses, but we're going to center on a very simplistic one. And we want to minimize the error or the empirical risk. The empirical risk on those parameters is the sum of the losses of a specific set of elements. This is a very big thing in astrophysics because minimizing the loss means that we're saying things like, if we have an observed data set of whatever, 100 or 1,000 galaxies, we want to generalize this to all the galaxies in the universe. So in astrophysics, that's a big thing. It's not easy to generalize if we don't have enough large data set. And having a large enough data set, we need machine learning techniques that are fast enough to process the data. So we're getting there. In practice, what we do is we have some data which has to be enough data. We don't know what enough is, but a lot of data. And we're going to split it in what we call training, validation, and test. So 80% typically is for training. It's those supervised objects where we know their labels, and we're going to validate it with a set of known labels, okay? And when we train this, we'll see what training really means. We're going to see, comparing training to validation, we see if we're overfitting. We're going to use very powerful techniques, and the problem with these techniques is they try to learn the data off by heart. They don't generalize anything. They don't get any general function. They just learn the input data, and that's a big problem in machine learning in general, especially in neural networks, okay? So we're going to use this validation set to see if we're overfitting. And then the big thing is we have a test set that has never seen the algorithm we're going to make here, and we're going to see if the predictions really make sense, actually. Because in the training validation set, there can be some confusion. The network might be cheating on us. It might be saying it's better than it really is. So that's why we have the training set, okay? So in general machine learning, we're talking about machine learning in general. I'm going to go to deep learning, which is what we want to talk about, is that we have, in general, a loss function that we've seen, something we want to minimize, and a way to minimize it, a minimization algorithm, optimization algorithm, okay? This is common to all machine learning. And what does this mean in the big picture of things? Okay, we have data science, which is a word that is not very fashionable today, but it still exists. A few years ago, everything was data science. Now nothing is data science, but it still is. I mean, this is data science. We're getting things from data. I mean, we're learning from the data, okay? And inside the data science, there's a term which has been misused commonly, which is artificial intelligence, which people on the street think that the machines think. It's not really the case. It's a technique. We're going to go into that technique and see what the myth is or not. But what we learn from the street is that everything is artificial intelligence, and it isn't. I mean, the large language models, which we were going to talk in the end of the lectures, are a big thing, okay? Foundational models, the transformers, we're going to talk about that. That's a big thing. But not everything is ChatGPT or making pretty pictures to harass people. I mean, the press is always talking about these large language models. And in reality, the deep learning, we're going to go into that, is being used in healthcare and cancer detection. We have a group working on that. We have autonomous vehicles that they learn how to drive by themselves. We're forecasting climate. We're translating language. We have dozens, at least, of applications which are much more interesting. We have protein folding, which has a Nobel Prize. We have lots of applications which are not just chat bots and pretty pictures, okay? So we're going to go into that a little bit later. What we're meaning by artificial intelligence is not what people think. And inside artificial intelligence, which is from the last century, the 50s, there is something called machine learning, which is a very powerful concept. It's that the machine learns by itself, okay? And that's a very powerful thing, and it's in data science where we want to learn from the data. And then we have, inside machine learning, we have deep learn, okay? Just to see what we are in machine learning, we have different algorithms in machine learning. I think you've seen a random forest based on decision trees or support vector algorithms with kernel algorithms. And there's also deep learning. I mean, the difference is this F, okay? Is the function used. How are we going to define that function? What way are we going to minimize the loss? How are we going to find the minimization of the loss, and which way we're going to do that? That makes the difference, okay? We have random forest, which is, there's a tree, a decision tree, could be like the Galaxy Zoo we all know about. It's a type of random forest, a type of decision tree. This is an algorithm to find something from the data. You put data in and you get some labels out, okay? Or you have the support vector algorithms, k-means, whatever. You have many ways to separate data, however nonlinear or complicated they are. And then we have what we want to talk about, which is deep learning, which is using these things, okay? These things are artificial neural networks, ANNs, okay? And the ANNs, those are blobs. I'm going to show you what the blobs are, actually. They are based on a very, well, it's a very, artificial intelligence by itself, we have to start in China 3,000 years ago and things like that, but we don't have to go so far. In Greece, it was 300 years ago or something like that. The humankind wants things that operate by themselves. It's a need. I don't know why, but we kind of like, in Japan, it's a big thing. We kind of like things that try to mimic our thinking, our actions, and maybe our thinking, okay? In 1950, the origin of all this, Alan Turing published The Computing Machinery and Intelligence, and he defined the Turing test, where you can test what the machine can cheat or it can simulate what the process of a human would be. I mean, when it's a test that if a machine passes it, it should work like a human. It's not really like that, because we've gone beyond that. But for 1950, that was pretty big thing. And the term artificial intelligence is from 1956 by John McCarthy in the Dartmouth workshop. And they defined the basis of all this, okay? The problem is, well, the start of this in 1958, Frank Rosenblatt, okay, a psychologist, he proposed the classic perceptron. The perceptron is a neural model that mimics the human neuron, the way the neurons work in the human body. In 1958, things were like this. It's a mess of cables, and it's no wonder this didn't work. I mean, they didn't have the technology to make this learn in a practical way. Okay, he was playing around with images and trying to get the outputs, and this FW, he was going to fine-tune the parameters by hand, by physical connections, and this was done physically. I mean, with electronics. In 1954, we have the first general computer, the IBM 704, which introduced Fortran and great languages like that we've all used, unfortunately. And it was no wonder that if things were like that, well, they didn't work well. They don't have the computers we have now, okay? And it's all based on this guy. This guy, Santiago Ramón y Cajal, it's one of our few Nobel Prize winners. He was the first person that said that the neurons are actually cells. They're individual cells in 1889, okay? That sort of thing which communicates between different cells via synapses. And taking this image and this idea, this Rosenblatt established the perceptron. The perceptron is just not a toy, but it's a very simplified model of a human neuron. Okay, the human neuron has a nucleus, has an action, has the terminals, and there's an impulse. Okay, well this perceptron, this is a mathematical description of the perceptron, has some inputs. Also has the X inputs. Okay, those are multiplied. These are very simple equations. It's just multiplying the inputs by something we call the weights. These are the features, okay? And we have a bias term. And then we have something which is very, very important, which is the activation function. It decides if the neuron shoots or not, or doesn't do anything. If it activates or doesn't activate, okay? And this is a function that's applied to the simple, more or less simple. You can have it more complicated. If you have a lot of inputs, it's a bit more complicated, but it's just adding things which we know how to do very fast. And if we have a lot of data, we need dedicated graphical units, which what they do is add things very fast. So that's one of the justifications for having this. But this this activation function, we need to talk about it a bit more, okay? Because this is where we're going, okay? They have the perceptron, which is blob, okay? And we have a lot of blobs. We have the input blobs, make the input layer, and then we have the output layer. And in between, we're going to have something which is called the hidden layer. It's another layer of more of these things. Surprisingly enough, this works. If you put this thing and feed it some input, and then you compare this input to what it gives with the output. In the beginning, we don't know the weights, we don't know the W's, we don't know the features. So we make them, we give it a random initialization. It's as good as anything. Okay, at least it's not zero. If it's zero, it's a big problem because then we're losing information. So we randomly initialize this, and then we have the forward pass. We find the outputs, we find the difference between what the outputs are and what they should be, because we have a labeled data set. Okay, and then we go back. We're going to see what that means with back propagation. We go back through the neuron network, through these neurons, to back propagate the information of how good or how bad the fit was, the difference between what the predicted and the real labels are. Okay, and having that, we adjust the weights accordingly. I mean, we balance the weights, so it improves. So doing this, the network learns. We're going to see a bit more in detail. Not a lot, because it's a bit hard, a bit tough, but we're going to see a little bit of that. And one thing we have to say is that this f, the small f, the activation function, has to be non-linear. Why does it have to be non-linear? Because if it's linear, it's useless, okay? How do we know that? Well, let's suppose it's linear, okay? And if we suppose it's linear, we have the input layers, okay? The I layers, and then two hidden layers. One hidden layer with two neurons, okay? And one output layer with two neurons, okay? So if we do the math, which is pretty boring, but we can do it, we have the H1 layer, the hidden one layer, is just a combination of the weights, okay, multiplied, and the bias, which is sum. Okay, you have to believe me in this. Don't follow it because it's a bit boring for this time of day, but believe me, it works. You do this, you do the math, you find the outputs, which are applying the weights, the W5 and W6 on the H1, okay, and H2, and you have the output weights, the output function, okay? And if you do this appropriately, okay, in the end, what you have in the output is just something which is multiplying the input, something else which is multiplying the other input, and the bias, which is exactly what we had in the beginning, a linear approximation, which we don't need. We know how to do linear fits, so we don't need such a complicated thing. In another way, if you have a linear activation function, you only have a linear network. which we don't need. We want to go non-linear, okay? Because we want to find non-linearities in the data, okay? So this activation function should not look like this, should not look linear, okay? If it's linear, it doesn't work. It just gives linear fits, so we know how to do that very fast. So we have to go for something looking like this, like the sigmoid, okay? In this case, there are different types. This is a very simple activation function, which this activation function introduces non-linearities in our process, which are essential to make the network learn the non-linearities in the data, okay? This is a sigmoid. If we normalize it, we have the softmax, we'll see in a minute. The sigmoid is just this simple function. It's very easy to differentiate. We'll see why we need that. And it brings the non-linearities. There are dozens of activation functions. For instance, the rectified linear unit. It's almost a linear unit, but not really. It's not to the left, if I get there someday, okay? And you have a linear value for the positive ones and a zero value for the negative ones. That's a modified rectified linear unit, which works. It works for very simple problems. Or we have something more glorified, which is the elliptical linear unit, which is not zero. The problem with becoming zero for small negative values is sometimes when you go back, you get zero learning. The weights go quickly to zero and the network doesn't learn anything. So we use these different, don't worry about the exact function you're going to use. Basically, people just use ELO or ReLU and see if it works, if not, change it. There are lots of things in machine learning where there is no mathematical demonstration of what you should use because it depends on the data and the type of loss the minimization you're doing, okay? So don't worry too much, just know we need a nonlinear activation function, okay? And why can we use, here is a mathematical theorem, okay? Why can we use a neural network? This is the assurance that we can use a neural network. There's this guy, Sibenko, in '89, that said that for any continuous function in a hypercube of 0 to 1, which is quite normal because we always try to normalize the data. The unnormalized data it's not very useful. We're going to use normalized data. If we have a hypercube to real numbers from 0 to 1, for every positive epsilon, where epsilon is the error, okay, there exists a sigmoid, that's what we talk about, sigmoid-based, one hidden layer neural network that obtains the minimal error in functional space. Okay, what does this mean? This means if in a couple of years afterwards, Horvik generalized this and said basically the same thing, but without the sigmoid thing, okay? He said, for any continuous function, blah, blah, a non-constant bounded and continuous activation function, that for every activation function that we're using at the moment, well, the same thing. We have a one hidden layer neural network that minimizes this error in functional space, meaning that a big enough neural network can approximate any smooth function, which is a great thing, because this is what we don't want to do. This is assuring us that, for instance, if we have a strange function, imagine that's the function. If we have our sigmoid, we just put another sigmoid, and we have our very nice Gaussian inside. Okay, if we do that a couple of times, we have 3 Gaussians, and we all know that 3 Gaussians approximate anything in astrophysics. So we're approximating. It's not the exact function, but it's good enough. That's what we're saying. We have a good enough approximation to our problem. Okay. What else? Well, it's not going to be as simple as that. The blobs are going to be in a layer. Okay. And this is a generalization of the neural network, okay, in mathematical formula. There are a couple of lectures from Stanford, which are very nice. I'm going to not really show, but I'm going to indicate, if you want to have a more mathematical background, they're going to explain it much better than this, because we don't have a lot of time, okay? But in a generalization, we have the activation function, the G, that works on the weights, the W, these are the parameters we were talking about, the inputs and the bias, okay? But then in this case, W, because we have many neurons in this first layer, W is an array, okay? And B is a vector. It has many values, okay? When Marina is going to talk about images, this is going to get a lot complicated. I mean, it's going to be a bit bigger. It's going to be a 2D array, and then it's going to be for each filter that you use another dimension. So it's a multi-dimensional problem, but the computers have no trouble in resolving this. But we're going to stick to the general formula. I'm not going to go very deep into this because it gets a bit messy. Okay, and then you have the first layer, which is just applying what we've seen, which is the formula, and this goes into another hidden layer. The hidden layers can be a different size. They can be larger or smaller than the initial layer, and there can be many hidden layers. In the deep learning is that there are many hidden layers that make this work, okay? With one hidden layer, it's hard to get something done. I could do it with a simple problem I was proposing at the beginning, but in general, you're going to need many hidden layers. How many? We don't know. You don't know until you do that. I mean, this is empirical. You have to trial and error, the size of the many hidden layers and the number of neurons of each layer. It depends. It gives you the number of parameters. If you're going to, it depends on the data you have, on the problem at hand. So it's very hard to say a general rule, but you have to try. So that's what we're going to try to give to you, some general programs that work with basic normal data, normal spectra, normal images, whatever, okay? And the result of the different hidden layers, which the result of one layer goes into the next, goes into the output, the last layer, in the same additive way. And in the end, you have the sigmoid, which is what we've seen with the softmax, which gives a probability in general. It's a prediction from 0 to 1 in what percentage in 0 to 1 or 0 to 100%, how accurate is the classification if we want to classify something, or what's the value if we want a regression. A regression problem is if we have a continuous so minimize the loss. So it's very simple. Well, it isn't simple because we have to find the minimum loss from an arbitrarily multidimensional function that we don't really know. So what do we do in physics? We don't do this. We substitute it with something simpler. That's what we always do. We take, for instance, the derivative, the Taylor approximation, and use the standard algorithms we all love, okay? We have the Newton-Raphson method, which uses the second derivatives, where we have the weights. The next weight is the previous weight, and then we have an equation that depends on something, which is the Hessian. The Hessian is a quite complicated matrix of second derivatives that we don't normally want to solve. It's great if you have it, if your loss function is smooth enough, but you don't know at the beginning. So it might work or it might not work. If it works, it's very fast, but maybe it doesn't work. So what do? We stay with what we call the first derivative, which is the gradient descent. Everybody stays. I mean, this problem of using the Hessian is a bit tough, even for computers, and sometimes doesn't work. So what always works is the gradient descent. So we go to the basics. The gradient descent, we only have the derivative of the function, and then we have the learning rate. The Hessian doesn't have a learning rate, but in the gradient descent, we have to establish a step. The step is what we're going to see the step in gradient descent in a while, is how big we want to go from the previous value to find the next. This is a minimizing problem. So if we have a 2D surface, we want to go, I think I have a plot here, okay? We have an arbitrary computer-generated 2D surface with two peaks, okay? So what do you do to find the minimum? You start from any point, you take the gradient, and you go the other way. So that's the typical way of finding a minimum. You're going to find the real minimum or the main minimum. We don't. You might get yourself lost in the secondary minimum, and then your results are going to be not very good. So sometimes we initialize this randomly, we initialize it many times, and we change the step. The step of this little ball here is the learning rate. If it's too big, it overshoots. It goes through the minima and it doesn't go into the minima. Okay, here in the minima, it's a bit overshooting in the exact peak because it's a very, in this case, it's a very specific point. But it gets to a point where there is a minimum. Okay, so what learning rate should we use? 0.01, like everybody says. Start with 0.01 and go beyond. I mean, if it's too big, then you get a smaller one. So this is empirical. There's no real way to choose the learning rate. Okay, and what we've talked about back propagation. Okay, we're going to try to get some intuition in the neuron, on a specific neuron, to see how we can find this. How the weights are changed depending on the output. Okay, you have the blob, the neuron. Okay, singular one neuron. Okay, and you have two activations, X and Y, and this neuron is function, the result of the activation times the weights and the activational function, and you have an output. This is the forward pass. Okay, and then what the neuron knows is its local gradient. It knows because it's inside the function. The dz dx on dz dy. I mean, the variation of how the inputs modify the output. This neuron knows how to do that because it's its own function. Okay, that's very clear, I hope. What we don't really know is going back to how the loss, this L, is modified by Z. Okay, and we want to know how X and Y have to change so this is minimized. Okay, so how do we propagate this derivative to X and Y? We use the chain rule. Okay, so strange sound. Okay, we use the chain rule. Okay, and we can always do this: dl dz dz dx. It's the same as dl dx. Okay, but we know these two terms. Okay, because we have the local gradient on one hand and the actual gradient at the end. Okay, and we've backpropagated this to how the loss is affected by X, by the inputs. So in this way, if we complicated this enough, we go do the same thing for the other input. Okay, and we have a bunch of other neurons in the net. If you do this analytically, you'll find how the gradients have backpropagated, how the weights have to be changed in order to the loss be minimized. That's an intuitional way. This is very well explained by this guy, Matt Mazur. You have it in the slides. I'm going to put the slides in my GitHub at least. So unless we find someplace better, and a little code I'm going to show you in a minute, where you can see this by hand. I mean, I thought it was going to be a bit tough at this time in the morning before coffee or to find this analytically, do it by hand. It's a bit, you can see it there. It's very nice. I mean, you can see how the loss is minimized and goes back and the weights are changed, the weights and the bias. But you can check it out. You can also check it out if you want some more background, the great Stanford course, the CS229, that talks about all these things in a more mathematical approach. Okay, more than I have time at the moment. I don't want to make this too large. This is my GitHub. You can check it out if you want. And what I wanted to show you is doing this. I mean, how do we do this? Just, I hope it works. It works. If it doesn't, there's no problem. So I'm going to share, if I can, something else, something completely different, like the multi-Python said. I hope I have something somewhere. I don't know where it is. Okay, I have to minimize some. I think I have a browser, but it's maximized. Okay. And I have a notebook. If not, it's in my GitHub. Okay. Let's see if I can see where I am at the moment. Okay, this is a Jupyter notebook. I want to share it, but I'm not sharing it actually. I don't know how to share it. Just a moment. Nothing is seen. This is the usual stuff. Let's see if I can share this screen. I'll shake a little Chrome. Oh, let's see. Here it is, I hope. Okay, this is. Let's see. Now, how can I? Does this? Okay, you can see it. Okay, this is the code. Okay, this is the code I'm showing you. This is how I built the data before. Okay, this is I have the Planck function, the usual constants. I mean, you can check it. It's very simple. It's a toy data set. Okay, it mimics at least the usual HR diagram or something like that. The star temperature versus the magnitude. It's something we also know for the cool stars. Okay, I built it with this data set. Okay, with this function. What's interesting is to be able to use a neural network to fit this. It's mandatory to normalize the features. Otherwise, it doesn't learn anything. The features in this space are very weird because our astrophysics are weird. We're weird. And we use logarithmic scales and very big ranges of things. So the networks don't really learn on that. They learn on things which are very close to zero, very close to one, between 0 and 1. So it's very typical to normalize this. You can see this. And we're going to build a simple neural network in Python. It doesn't matter if you don't know much Python, okay? This is a plain Python. Nobody uses plain Python for this, but I do because I'm crazy. And normally we use TensorFlow or PyTorch, which are these frameworks, which you can do this in 2 lines of code, okay? But that's not the point. I mean, when I give you the code, I can give you those 2 lines. It's no problem. But I wanted to show you that this is doing the math that we wanted, okay? We have something called the error, okay? The difference between prediction and the true value, okay? And we're doing this math, which is just the weights, okay, are generated by the previous value plus the gradient. Okay, this is the gradient descent in practice. You can look at the code. It's very simple. It's recursive, but it's simple yet. And there's no activation function because I wanted to show the problem that doesn't work. I mean, if you don't put an activation function, what do you get? If you train it, you have the forward pass and the backward pass and everything. I mean, you can see the functions are very simple. You can train it on the data, and what do you get? You get nothing. Okay, well, nothing. I mean, you get a straight line. You get exactly what we knew how to do, a linear fit, which is useless because we know how to do polyfit much faster than any technique. Okay, the only thing, the training, we see the training loss, how it's gone down, but it's not saying anything. It doesn't need a lot of training to do this silly straight line, which is exactly the same as the straight line of a linear fit, which is very reassuring to know that it doesn't work, but it doesn't work correctly. I mean, it's doing what it should do. It's doing a straight line fit. Okay, so we want to go beyond the straight line fit, okay? Then we introduce an activation function. I'm going to use a very simple, maybe too simple activation function, so you see it. This is the ReLU function, which it was the equation before. It's 0 and then it's a straight line for the positive values. You have its derivative, which we're going to need for the backward pass. Okay, if anything was clear from what I said before. And you have the usual equations. It's a bit more complicated because you have the really derivative in between. The activation function gets in between. And in the end, if you train it, believe me, you train it. Well, there's a couple of tricks here I can tell you later. And then if you train it, what it gives this. I don't know if you can see it because it's a mess. I'm not sure if you can see it. Okay. I'll zoom into one of them. Well, the linear fit is still the straight line, but the neural network, it's giving something which is following the data. We don't know how good or how bad because I'm cheating. I'm not giving training and validation data. And I'm cheating twice because it's only 200 points. That's not big data. That's nothing. I mean, well, I'm not using enough data, but it's a toy example, okay? This is how the loss goes down. And this is the difference in purple, I think, the residuals difference from the predictive values and what it should be. It's quite good. The neural network I'm using is one hidden layer with 8 neurons, which is really, really small. That's really toy problem, okay? So it's no wonder it's not very good, but okay, it works. And what's good to see, maybe you like it, it's the hidden weights. This is the weights that these neurons take at the end. So with linear, simple combinations, you can get a nonlinear output. Some people say that neural networks are black boxes. They're not black boxes because you can see in them. What you see, maybe you don't like it, but you can still check it. So this is the check. Maybe this doesn't make sense. No, it doesn't really. What it makes sense is the result. Okay. So what I wanted to show you, well, this is I'm zoomed in because you can hardly see anything on the rubbishy plot. I was helped by Claude, another large language model, to do this, which is very nice. Here you can see it in a thicker line, how this function, which we don't know analytically what is, but the neural network has fit this function, and it has fit it in not a strange way. It follows the data, but it follows it with a couple of kinks here in a way that the humans would not do. I mean, by hand we would do it softer, maybe, but the neural network, that's what it's been trained on. It's been trained on all the data that you shouldn't do. Okay, that's not how it's done. So I don't know if I check to, okay. If I do the same thing, but splitting the data between what I said before, the 200 points, okay? In 80% in training, 10% in validation, and 10% in testing, I can see what's going on. And I can see in the training loss, the loss obtained on the, I don't know if you can see it here, in blue, or blue or purple or whatever, in bold color, okay? The training loss is going down continuously, but the validation loss is becoming constant. That's indication, because it's larger. The validation doesn't go down and it's constant. And while the training is learning the data off by heart, the network is overfitting, okay? But it's no wonder, because I'm only using 200 points. So it's a toy problem. I can put more points and check that this changes. I don't know if I can do this in the Jupiter I have, but you have to believe, okay? The data, well, the result is basically the same. Well, it's basically the same because I haven't changed anything. I've only used the old data in blue and then the training data somewhere in blue. No, training in blue, the old data in cyan, or you can't see it, and the validation of squares. Okay. If I may, I don't know if I can, you can download these Python notebooks are in my GitHub. If you go somewhere here and say, instead of 200 rubbishy points, you put 2000, okay? And you press this button and hope it doesn't blow up, which sometimes does. If it didn't blow up, so that means the Jupyter's working. Okay, it's working. Amazing. It's one of the burros in Donner, I think. Okay, you have many more points. Okay, this makes more sense. These are 2000 points. It's the same thing. Okay, I'm showing you the same thing, just running the code again. And in the end, it's basically the same thing. In the end, what happens is a bit nicer, okay? You have more points, you have more data. And what's going on? There's no overfitting. Here, the training and the validation loss go hand by hand, and they're very close, okay? The validation loss doesn't stay at one value, and then the training goes down. They go down more or less the same. You should stop somewhere, because otherwise it's overfitting. Also, because even a simple network like this can overfit. If you put more hidden layers, it surely will overfit if you have so few points. Okay, that's what I was going to show you. So the takeaways from all this should be, or I hope they are, Let's see if I can share it again. My talk somewhere. I don't know where the quote talk is. Okay, here it is. Here it is. Okay. See if I can share this thing. What is this? Google Chrome. I'm not sure if this is the same. Okay. So here we are. So it's coming in the end. These are the plots, just in case the Jupyter didn't work. Okay. So takeaways from this. It's late enough. Deep learning is machine learning, and it uses artificial neural networks. There are many hidden layers. I mean, it's deep for a reason. We're going to see with in later lectures that it's deep. I mean, you need not like the toy example I'm showing you is just a playground to see that a simple neural network, simple hidden layer with 8 neurons can fit something nonlinear, okay? But many hidden layers are needed for deep learning, okay? It needs nonlinear activation functions. We know why that is. And we have to minimize the loss. We use gradient descent and things like learning rate and backpropagation, which I hopefully have got through. Okay, normalize the data is necessary. I mean, in coming to this point, I'm going to tell you that making a neural network, 80% of the work is working with the data. It's getting the data, normalizing the data, doing stuff with your data. The rest is much easier. It looks complicated, but it's not. Well, it depends what you're doing. If you're doing really, really complicated things like the guys in the IAC-DEEP, then it is complicated. But normally, you're going to spend a lot of time with your data. So, which is it's reasonable. I mean, this is big data. I mean, you need to process the data, right? And you need lots of data, basically. And that's it. Thanks a lot. Thanks. Any questions? Or in the chat or here in the room? Yeah. Let's see. I think this works. So people can hear you.
Thank you, Carlos.
Thank you.
I have a very, very naive question, and I think I might know the answer to it. But
Great. I love those.
so what happens when you ask the algorithm or the system to extrapolate?
Yeah,
beyond
it depends.
Where you have data.
If you're close to the training set, it might give you good results. But what is close? What does close mean? I mean, we're always told that extrapolating doesn't work, and it doesn't work. I mean, if you go far beyond your training data, the exponential functions are exponentially wrong. But if you're close to the data, you might get, I did a few things like that, doing interpolation and then going a bit further away. And because neural networks learn the non-linearities in the data. That's what we're saying today, or in deep learning. And that's true. And so if you learn the non-linearities, you learn them between the data and a bit farther away. It's not like, I mean, these non-linearities are learned if you're close enough to the data. But how is close enough, you don't know.
And the second question I have is, here you have presented a pure data-driven, of course, approach to understanding data. But, sometimes astrophysics, what underpins astrophysics are physical systems, but you have some physical constraints, say conservation of energy, things of that sort. So is there any way to implement?
There is.
This information?
You can do physically informed neural networks, which I don't know a lot of. There are people in the group that know a lot. I hope they're going to give a talk where you impose physical constraints in the minimization process. So you make the data, minimize the loss, but then having into account these physical restraints. You can do that.
Okay.
That's a big topic.
Thank you.
Thank you. Anyone else? In the chat? Don't be shy. How many are there in chat? Any other question? Okay, well, thanks a lot. See you in the next by Marina. Thanks a lot for coming. Thank you.